Welcome, everybody. Let me remind you, no laptop rule. Please, no laptops, no handguns in the lecture theater. Thank you. All right. Can I just point out, I got it to work. It turns out, actually, the new MacBook Pros have a problem, a known problem. They don't work with old projectors. But this is VGA, so this seems to be working. All right. This is good. All right, good. One quick thing. So I told my students that a lot of people like Python. My TAs, apparently they were right. Like it was close, but it was, you know. But one thing I forgot to mention, Julia has the same syntax as MATLAB. So if you know MATLAB, you also know Julia. Does that change things? Yeah. Okay, who's in favor of Julia now? Oh, here's a noise. Come on, yay! All right. Comparison, Python? All right, still a tie. All right. All right. Well, at least there's some excitement now about Julia. I spent all Christmas week, you know, vacation doing it. Okay, good. So what we got left off last time was what is machine learning? So I don't know if people recognize this guy in the background. This was actually my motivation to go into machine learning. Was I want to have my own Terminator to beat up my brother. So that was, you know, when I was 15 or something. Still working on it. Okay, good. So let me just give you a high-level overview of my view of what machine learning is. So basically, you all know traditional computer science, or at least you know something about it. And in traditional computer science, you have a computer, which is this thing in the middle, and you have some data, which is the input. And so the data could, for example, be an MP3 file, right, or some music file, some video file, or something. And you want to generate some output. And where the programmer comes in, the programmer writes a program that basically takes the data, the input, and generates output out of it. So if you, for example, want to play a music file, an MP3 file, well, you know, given that you've taken a programming course before, right, how would you do this? Well, you would look up on Wikipedia what are the specifications of an MP3 file, and then you would sit down over a long weekend, and you could probably write something in Python or in C, right, that basically takes the file, decodes it, generates the waveforms, and so on. And it's not a big deal, right? After a couple of days, you will have a program that takes that data and generates the output. That's fine. That's not the kind of problem that I'm confronted with as a machine learning person. So the kind of problem that I get is something like this, right? So someone comes to me from the med school and says, here I have this fMRI scan of this person, and I would like to know if this person has Alzheimer's, yes or no, right? And the problem is there's no Wikipedia page to look up how to generate, how to extract that information out of, an fMRI scan, right? So if you're the programmer at this point, you're not so happy. But it turns out it's a very specific type of problem. So what I can do is I can say, well, I can't really help you with this particular image yet, but there's something else. Right? So if I ask the physician to go back and basically look at the past files and look at fMRI images that he or she has collected maybe 5 years ago, well, let's say within the last 5 years, it actually has become apparent if the person has Alzheimer's or not. Right? So you can take the past images that you took from people a long time ago, and you can now annotate them and say, well, it turns out this one did have Alzheimer's and this one didn't. Okay? So what I can do is essentially I can collect data for which I know what output I want. Right? So I say, this guy, basically, here's an fMRI scan of a person. The answer should be yes, he has Alzheimer's. Here's a person, she does not have Alzheimer's, etc. And that's exactly when we can do machine learning. Right? So machine learning basically turns things upside down. As input, you stick in the data and the output that you would like to know, like you would like to have for that data. And the machine learning algorithm then crunches this data and outputs a program, right? Which, if it had given that data as input, would generate that output. Okay, does that make sense? So basically, in some sense, we are replacing the programmer. And this program sometimes literally can be C code, right? Often it's not. Often it's some numbers because that's just more efficient. But you can convert this into, into C or whatever programming language code you have, it's usually not very pretty, right? It's very long and cryptic and so on. But it is, you could go through it and it makes sense. And then, of course, we do the obvious thing, right? We go back to this doctor that came to me in the first place, and now I have this program, and now I stick in the data point that he actually or she, wanted me to analyze, and now this program generates some output, and that is my prediction. And we call this part here training, and this part here testing. All right? Any questions? We will go through this in much, much more detail in the future. And by the way, just one warning, this is the last PowerPoint slide I will give. After this, actually, everything will be Blackboard. So this was initially, when people came up with this seemed like a crazy idea, right? Can you even do this, right? This, like the program the computer basically programs itself, right? It seems nuts. But it turns out, over the years, it really, really works. And nowadays, actually, what's fascinating about this is, A, you can write programs that basically, would be a lot of work to write, and now you can make it automatically. But on the other hand, and that's the most fascinating part, you can write programs that you don't even know how to write. But you can generate programs that you wouldn't even begin to know how to write that program. So machine learning was formally introduced. It dates back before this. But the first formal definition that I'm aware of comes from Tom Mitchell in 1997. So he wrote, and let me just read this out. A computer program A is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at task and T as measured by P improves with experience E. Got that? The short version is algorithms that improve on some task with experience, right? That's also, without the E and P and, that's very, very simple, right? Why does this improve? Right? If you go back here, where's things improving? Well, if I give this more data here, I can basically generate a better program, right? And I would do better. Okay, so that's the idea. The more data I give it, the better the program is, and that's why we call it learning, right? Okay, let me go through a little bit. Let's just walk down memory lane and give you a little bit, before we dive into how to do this, a little bit of a history of how this all started and where it came from. So arguably, the very, very first, well, there's some dispute, but the first algorithm that learned from experience was Samuel's checker player in 1952. It wasn't really kind of what we would consider machine learning now, but it was basically the first time someone came up with the idea to actually learn, basically to store some moves in the database, and actually as you play more, you eventually get better. Checker since then actually is a solved problem, so it was a benchmark for AI for a while. So by the way, this time there was no mentioning of machine learning. Machine learning did not exist yet. So the field first actually, there was at this point, at some point people at first called artificial intelligence, and eventually machine learning emerged out of this. The checkers actually became a benchmark task for AI for a while. Turns out actually there was a world champion of checkers. He was amazing. He was probably the best human to ever play. There will never be someone who plays checkers that well. He was undefeated for over a decade. It was like no one was ever close to him. And the big dream of the AI field was to finally beat this guy. And they tried many attempts, and turns out he always beat the computer. And eventually, actually, I forgot which year exactly it was, they finally had a program that beat him. And he died very short thereafter. And so I looked into this. And turns out, actually, it's not a coincidence that he died very short thereafter. It turns out, actually, he had terminal cancer. And he, at the time, basically, he was already in his deathbed. He was in a hospital. He was dying. He only had a few days left. And someone rushed in and was like, beat this computer program. And then when they beat him, like, oh, yeah, you'll take this. So I don't know. I feel like that's it's kind of a dark point in the history of AI. Like, could have let him die undefeated. Like really. Anyway, checkers is actually now a solved problem. So for any single position, there's the optimal position. The optimal move is worked out, and white will always win. Right? So it's no longer a challenge. It's not a game in that sense. What I would call the first machine learning algorithm actually comes from Cornell in 1957 by Frank Rosenblatt. So he invented the perceptron, which was is something we will talk in very, in detail. I will devote a whole lecture to it. But this is really an algorithm that is still used today and was really revolutionary at the time. And ultimately, this is what an artificial neural network or what deep learning is today. So there's actually very little difference to what he invented back then. So he had this, basically, his insight back then is, was basically 90% of the way there. So he, what he was really missing was computational power. So he did not have the large computers that we have nowadays. So he was really a visionary. And this is an ingenious algorithm that we will talk about very soon. At the time, though, one thing you have to keep in mind, this is, I will not talk about this too much, but it's basically he could only train very, very small networks because he was very constrained by the speed of computers. Now, it's 1957, think about this. Probably all the computer power of the entire world is less than your phone, right? And so what he mostly analyzed was like a single layer perceptron, which is a very, very limited algorithm. But when this came out, there was a huge, at this time, there was a huge excitement about AI, right? Because this was something new, right? Like algorithms that could learn from experience, they could play checkers, right, to some degree, right, and so on. So people were really, really excited. There was a lot of funding for it, a lot of funding research, and generals were already dreaming of armies of robots, etc. This is what generals do, right? They dream about this kind of stuff. I have nightmares of that kind of stuff. But but it turned out, actually, it was a little bit too early. So what happened was something called the AI winter. This was the AI boom. People were really, really excited. It was the first AI boom. People were really excited about AI when this came out, and everybody was talking about it. There was articles in the newspapers and so on. And then came a book by Minsky and Papert. And I don't think they had the intention to kill AI, but they did. And they actually analyzed these algorithms, and they came up with a very, very simple data set that everybody could understand. It's the XOR data set. It's very, very simple. You can draw it on 2D. And they could say that the perceptron, as Rosenblatt shows it, the single layer perceptron, can never learn that data set. And it seems so simple. It's basically just 4 points. They could, 2 are positive, 2 are pluses, 2 are circles. And they could say you could never actually learn to distinguish between these. And it seemed like such a simple thing that everybody understood, wait, if they can't even learn this, right, how can they ever become killer robots, right? Like, there's a disconnect here. And so what happened is actually funding for AI collapsed, like, drastically in the United States and in most countries around the world. So this is called the AI winter, and people still refer to this. It's basically when people got really disillusioned with AI. So then what people did is they said, well, wait a second, we don't do AI, we do machine learning. It's totally different. And you should fund that. It's the same people, but so that was really actually kind of, and this is a sarcastic way, but it's kind of where I came from, right? So, but to some degree, the fact that if some research area dies, there's also a moment for basically new approaches, right? That maybe beforehand weren't taken seriously because it wasn't part of the way people thought, right? It wasn't along the lines of people thought. Suddenly, new approaches were taken seriously. And that is essentially how it would place machine learning. So on one hand, if you want to get funding, you have to say you have to do machine learning. But on the other hand, actually, there was also a difference. And I would say the difference is twofold. So number one, AI we're very focused on the human. Right? It basically said, like, we want to build something like a human. And it was very focused on problems that humans think are very, very hard and try to solve them with algorithms. Machine learning is more the bottom-up approach. So you start with a computer, and it's more like basically what I told you earlier, right? You basically try to find a program, try to learn something from data. There's not really, machine learning per se does not really have the ambition to create humans, essentially, or create something like a human. Right? It can be a very different approach. And that's very freeing, right? Because you can do things that, well, that's clearly not what's going on in the brain, but it works really well on these kind of, on computer hardware that we have. And computer hardware is very different from the human brain. Another thing, and that's very, very important, is that machine learning focused on statistics and optimization and not logic. So, computer science traditionally is very entrenched in logic, right? There's a very strong connection between, most algorithms, right? The way you argue about algorithms is through logic. And that is, that was a natural choice to think about AI. And if you look at old movies like Star Wars, etc., right? The way AI, is presented is as completely logical beings, right? Everything they say is like C3PO is always logical, right? Because that's how people thought AI are. Actually, to be honest, if you read these old papers, some people thought that at the time that humans are completely logical, right? Like, someone in the brain, everything is very. Obviously, they didn't have many friends, but. It seemed like ultimately the wrong approach, right? And people tried, at some point there's like people inventing fuzzy logic because they realized you have to have uncertainty, right? Sometimes we have beliefs about something. It's not, you don't have a clear truth. Like it's, people basically made these statements like, is the light on? Yes or no? And if the light is on, then I don't do anything. If the light is off, then I switch the light on. Right? But sometimes you're not sure, right, about something. And the right approach to do that is really statistics. I mean, statisticians have dealt with uncertainty for generations, right? So beforehand, that wasn't really taken into account. It was, I'm not saying AI is not all statistics, is not statistics at all, but machine learning was definitely a much more statistical and optimization-based approach. Okay, so there's a very interesting point in 1994 where I would say this was a pinnacle point because it was the first time that people really kind of realized how powerful that idea is, right? And that it really works. So you have these moments in time. Researchers are working on things, and they're in their own bubble. But occasionally, basically, people around the world notice what's going on. And that one of those moments was in 1994, where Jerry Tesaro from IBM wrote a backgammon player. So I don't know if people have heard of backgammon. It's actually a very, very popular game around the world. In almost every country except the United States. Here, people don't play it. But it has a huge following in huge parts of the world. It's very, very competitive. There's world championships, etc. And what Jerry did is he wrote a program that basically would just check if a move is legal. And that's easy. And then he, at the time, the way people thought game playing works is you use the minimax algorithm. And those people have taken AI. They know how this works. Basically, what you do is, if you play checkers, you would do this. You basically say, well, you go through every possible move that you could make, and you say, if I would make that move, what would my opponent do? If I was the opponent, I would make that move. Well, what would I do? I would try this move, etc. And you always flip the board. Right? At the end, you say, well, who looks better now? And if now my opponent looks better, then that's a bad starting position. And if I look better, then that's maybe a good move. So he did something else. He instead took an artificial neural network, which is basically what Rosenblatt invented in 1957, and he let the neural network make the decision which move to choose. So he said, here's a list of all possible legal moves. The neural network chooses which one to play. And so when he did this, the algorithm made totally random moves, right? Like, clear, didn't work, right? Didn't do anything. But then he did something really, really cool. He took the network and he let the program play against itself. And so you had two copies of the same program, and they let it play against itself. At the end, one of them wins, right? They're pretty random, right? Make pretty random moves, but one of them wins, and you tell that one what you did was good, and the other one you lost. What you did was bad, right? So basically, it tries to reinforce the network to do whenever you get positive feedback, you try to do that more. And when you get negative feedback, you try to do that less. And so you had that feedback loop, where you basically just let this run, and then he went home. And he let this thing run and play against itself. And he lets it run overnight, whatever. Next morning, he comes back. He takes the program. He tries to play against it. And he loses. The program beats him. And overnight, just playing against itself, right, with no other input, has learned to play better than he did. So he goes around his office, right, and challenges other people, like, play my program, right? And it beats every single one of these people. So then he gets really excited, right? So what he does is he calls the world, the organization for the world championship in backgammon. And he says, like, I have this program, and it can play really, really well, backgammon really, really well. And I would like to challenge the world champion. And so they were okay. They were curious, and the world champion was interested. And so they actually made an appointment, and they played against each other. And in the meantime, by the way, he let that program play against itself a couple 100,000 times, or 1 million times. And the two had a face-off, and the program won. And that was something that took people completely by surprise, right? And people go up to him afterwards and was like, well, that's amazing, right? How does the program do it? And he's like, I don't know. Because it learned it itself. In fact, Jerry, is not such a good backgammon player, actually. He actually told me, I talked with him about it, and he actually said, well, afterwards, right, because then he had to talk so much about backgammon and so on, he actually started to get really into it. But at the time, he really wasn't a good player at all. Right? The program was much, much better than he was. And without him actually putting any of backgammon knowledge into it. And in fact, the amazing thing is that during that face-off with the world champion, his program made a very interesting move, a very interesting opening that the world champion thought was crazy. It was not a good move at all. And so, but it turned out it was actually a very good move. So the world champion actually asked for a copy of that program and started analyzing it, and then actually realized that's actually an opening that was undervalued. And actually, it turns out there was a new opening that basically this program discovered, and it's now actually in the backgammon books. So after this happened, his bosses at IBM were really excited, and they were like, "This was awesome, but why did you choose backgammon? No one cares about backgammon." So they did, let's do chess. And so they, again, this time they put a big team together and a lot of resources, and they challenged Garry Kasparov, the world champion at the time, and probably one of the best players in the history of humankind. And there are 2 matches against him in the second match, actually. The first time, Garry Kasparov won, and they challenged him again, and the second time, Deep Blue won. In all fairness, actually, this was less of a learning approach. This was more of a minimax, traditional AI approach, because they played it really safe. But the evaluating if a position is good was learned. Now, machine learning is everywhere, and you may not even know it. Right? This here is a search engine. This is Yahoo. I don't know if you've ever seen it. So, search engines, for example, right? When you think about what search engine is a completely ridiculous problem, right? We have billions of web pages, and you type in 3 words, and you expect, based on these 3 words, that the search engine knows which one of these billions of web pages you want, right? Clearly, that cannot work, right? But it does. How does it work? Well, the reason is that humans actually have very predictable expectations, right, of what you want to see, etc. And a lot of web pages are not very interesting, etc. And so the way this actually is done is actually learned. So with Google and Yahoo and Bing and so on, what they do is they employ hundreds and hundreds of people that actually go through search engines. So basically, whenever you search something on Google, there's a small chance it gets to one of these people. And what they do is they actually label web pages and say, this was a good answer, this was not a good answer, this was a good answer, this was not a good answer. And then they basically put all this into a big learning algorithm. The learning algorithm then learns what's a good answer and what's a bad answer. Of course, spam filters is a great example for something that it's really, really hard to write a spam filter. Right? It's almost impossible. Right? For two reasons. A, what is a spam email? Well, a spam email is an email that you don't want. Right? Well, what does that mean? Right? Well, clearly some people want these emails, right? Otherwise, it would respond to these emails, right? So, for example, emails about stock, right, or stock options or something. For me, it's always spam because I'm not really interested in this. But I know someone who's actually, in finance, right? Well, for them, actually, it's not, right? And you can also train your spam filter. Whenever you get emails from your mother-in-law, right? You can just spam, train it to say that's spam. So whatever you think is spam, right? It's a very, very subjective definition. That's one problem. The second problem is that the moment you would write a spam filter that's hardwired, and so basically say, like, whenever you, for example, the word Viagra, right? I don't know, this is some, I don't know what that is. This is some spam, but like for a while there was a lot of Viagra spam. And so, it's a very simple rule would be, but whenever you have the word Viagra in the email, that's probably spam, right? It's very rare that people actually, email people, I love Viagra or something, you don't really do that. But maybe some people do, but that doesn't work, right? Because the moment you do this, then the spammers would just misspell it, right? So they basically spell a 1 instead of an I, or they put something slightly different, and then you still get the message across. Because it's adversarial behavior, right? So people would actually immediately then change the way they're spamming, and now you have to rewrite your whole program. The nice thing about learning is you just take the new data and you just retrain it, bam, right? 5 minutes later, you have a new spam filter that actually is now adapted to the new way spam looks. Or you can actually do online training that basically that's the way video works, is every time you get a spam email, you train it a little bit, and so it always keeps up to date. Another example here is news, right? So Google News actually learns what you're interested in. Apparently, I'm interested in Lindsay Lohan. Well, I guess that's not true, but so it will learn your patterns, right, and basically suggest news stories to you. And so one thing, that I guess a lot of people talk about, there's also a lot of research here at Cornell, is, for example, self-driving cars, right? And so that's also something that really, I think, a big part of why that is possible now is actually through machine learning, right? So a lot of the sensors have been around before, so there are also some new developments. But the fact that actually you can basically, learn from how to drive a car safely really kind of was a game changer in this respect. And this is something, by the way, where I was surprised. So I remember a couple of years ago, someone asked me, maybe 10 years ago, someone asked me, how far are we away from self-driving cars? And I was like, it's going to take 50 years. And next year, basically, people started driving around with these things. So, and the reason is actually because suddenly a lot of things come together, right? So suddenly you get these leaps, because suddenly a lot of little problems get solved, and then you put them together, and suddenly you can do something big. When will it stop? So there is, of course, we have this carrot that's kind of dangling in front of us. That's the human brain, right? So the human brain really just is a big computer. It's just a very different hardware. But we know humans are really, really good at learning. And the principles are very similar. The actual implementations of the algorithms are very different. But the good thing is, we know we're not even close to that, right? So we can't do much. Some people claim this nowadays, that deep learning is now better than human brains. I completely disagree. They're very good at very specific things. So you can train deep nets to be, if you have a very specific task, you can train an algorithm to be better at that. But humans can do so many things. So that's certainly, in some sense, good news. That keeps me employed. And so that in some sense means there's still a lot of, we still have a lot to do, a lot of opportunities. The other thing is machine learning now is, the breakneck speed is being applied in all sorts of areas. So people now in biology and chemistry, et cetera. Like 10 years ago when I got my PhD, and I talked to people outside of computer science, and I told them I did machine learning, nobody knew what that was, right? Like, they thought of building machines or something, this was something that was completely unknown. And now people in biology, chemistry, you tell anybody you do machine learning, and they all go like, oh, okay, yeah, we should talk. So it's basically now, suddenly, people in fields that have nothing in common, right, use the same algorithms to analyze the data and make predictions. And that's extremely powerful. It's still very hard to design machine learning algorithms. And there's not many people who can actually design new algorithms that are meaningful and useful. It's a small community. But there's many people who can use them. Oh, wait. Yeah, I have a little more. OK, good. So let me just talk about what are the different types of machine learning there are. And there's, very roughly, there's 3 types of machine learning. There's supervised learning, there's unsupervised learning, and reinforcement learning. So this class is really only about the first one. So in this class, we will talk about supervised learning. Supervised learning is exactly what I just told you earlier with the fMRI images. So I give you data, and I know the answer to that data, and I would like to have a function that goes from that data to that answer, to that output. For example, spam filters and search engines, etc. Unsupervised learning is when I give you data, but I have no labels. I just say, like, here's some MRI images. Do you think there's something interesting going on here? Right? Maybe you can find some patterns that repeat or something like this. There's the class machine learning for data science is mostly covering this. And that's basically, we're alternating these 2 classes. There's also reinforcement learning. And reinforcement learning is when you do something for a while, and at the end you get feedback and say, that's good or that's bad. And that's what Jerry Tesaro used for his Backgammon algorithm. So that's mostly covered in the AI course and in the robotics course. Also, there's a significant overlap in the methods that we're using. It's just the way the feedback is incorporated is different. Apparently, machine learning is the #1 skill that employers wish for these days. Unfortunately, I don't remember where I got this from. So someone claims that on the internet. So but there was a list of 12 IT skills that employers can't say no to. A few quotes that are now a little bit old, but Bill Gates once said a breakthrough machine learning would be worth 10 Microsofts. I'm waiting for that one. Machine learning is the next internet. Machine is the next hot thing, and so on. Web rankings today are mostly a matter of machine learning. So that's really true. Machine learning is going to result in a real revolution. Machine learning is today's discontinuity. All right, good. That's the last slide, and from now on we will switch to Blackboard. Any questions about the stuff that I just said? No? Good. All right, so while I do this, I can hand out notes. So the way we will do this is, I really don't like it when people take, I write something on the Blackboard and then, the entire class writes down what I'm saying and then no one pays attention. So what I'm doing is I give you exactly my notes. So I have no information advantage in some sense. So we can just pass these back. And feel free to annotate. There's a downside, sir. You get my notes and my handwriting. And I apologize right now. The minute you know what I'm talking about. Very good? All right. OK, so we only have 15 minutes today. But let me get started on, let me at least get started, I guess. So, this is the headline of the entire class, actually. So the entire class will be about supervised learning. And what I want to do at least today is to formalize the setup. So what's the high-level goal, and what have we given, what are we trying to do? And let me just write this down in mathematical notation and give you some basic terminology that we will use throughout the course. So make sure you familiarize with this, yourself with this, because this is exactly the stuff we will be using the entire class. So, so on a high level, what supervised learning attempts to do is make predictions from data. So the setup is you're given a data set, and we call this D, of data points and their labels. So we're given n pairs of points, where my x is my data, and y is the output that I would like to generate. We call that the label. We call that the feature vector. So in terms of spam filtering, that would be the email. And this here would be, it's either spam or it's not spam. All right, so, or in terms of stock market, right? This here is basically some features about a stock, and this here would mean up or down. Right? You're trying to predict does a stock go up or stock go down. So these data points are sampled from some distribution. And so we have xi, yi, a sample from some distribution p. P is it's a distribution that we have no access to. It's a distribution that only God herself knows, right? It's basically where the data comes from. Right? If we had access to this distribution, then everything would be easy, but we don't. Right? There's some probability distribution that if I would pick someone here randomly and take an MRI scan of that, their brain, I basically get, you get an MRI scan. If I would do this repeatedly, right? There's basically some distribution of MRI scans that I get with that process. Okay, it's some strange distribution. It's from Mother Nature. Okay, and we observe data from this. Or in terms of emails, this is the distribution, from which emails are sampled. So everybody may have a slightly different one, right? So some people sign up to some newsletters, etc. So that changes the distribution of the emails that arrive in your inbox. Okay, and so what we would like to do is take data from this particular distribution and learn a function that basically goes from x to y. Okay, any questions? All right. So this kind of data is either, there's multiple cases. The most common case is either it's a time series. For now, let's assume it's not a time series. For now, just assume these are IID. So these are drawn IID. Anyone know what IID stands for? I think all of you together got it right. Who knows it? Raise your hand. Yeah. That's right. That's right. So they're all from this distribution P, and basically knowing one of these won't tell you anything about the other ones if you know the distribution. Okay, good. So what are these x's and what are these y's? So let me just quantify this. So these x's come from a space which I call curly x, and the y's come from a space called curly y. And so in this class, the x's are typically a d-dimensional space of real numbers. So basically what we're doing is we take our data and we summarize our data as d numbers. So it's a vector that has d numbers. And that summarizes everything we know about this particular data instance. Okay, so in an email, you could, for example, imagine these are the words of the email or something, right? And I will show you in a minute how to do this. So for now, we assume you can always do this. Right? It turns out very, very often you can do this. In fact, if you think about it, if you store your data on a computer, well, your computer, what does it do? Right? It has a long file of numbers. Right? Well, that's a vector, right? Of length d. So you know it's always possible somehow. All right. So we just call this RD as real numbers, and it's d-dimensional feature space. That's what we refer it to. And the xi is basically a vector that represents the ith data sample. So the ith email or the ith MRI scan. Yi, by the way, can you read this in the back? Okay, not so good. You know what it's the bigger chalk. Okay, I will try to, remind me tomorrow morning to bring bigger chalk.
Okay, I'll remind you.
All right, okay, awesome. So yi is out of the label space curly y, and that's basically the answer that you would like to know. Right? So it's either, for example, this is spam, this is not spam, etc. Okay, let me give you some examples for what y can be. Let me, how do I do this? Oh, that was a close one. All right. Okay, let me give you some examples. So for example, one is binary classification. So examples of y. So binary classification is curly y is either 0 or 1. Or you can also write it as -1 or +1. And so an example here would, for example, be email spam filtering. Right? Where you basically say -1 is spam and +1 is not spam. So you have exactly two options. And for every email, it's one or the other. Another option is, for example, face detection. You take an image. Is that a face? Yes or no? Right? So your camera does this. It detects faces. There's a little window that goes over the face, over the image, and tries to find a face. This is one of the most common settings in machine learning. Another one is multi-class classification. So here, curly y, you have multiple classes. So I call this k different classes. So it can be 1, 2, 3, 4, 5. right? So let's say, for example, one option would be that I take articles on the web and I would classify them as either sports, or politics, or about gadgets or something, reviews or something like this, right? So basically, you have different categories, and you want to know, for example, Google News, right? They ask you, are you interested in entertainment? Are you interested in politics? Are you interested in tech news or something, right? And so what they do is they go through the newspapers of the world and they classify each article that just came out as one of K classes, right? But one may, for example, be sports, and K is politics. Any questions about this? Raise your hand if you're with me. All right, awesome, good stuff. Another one is regression. And regression, Y is just the real numbers. That's one way of doing regression. So here, you don't differentiate between different categories, but you try to hit a specific number. So for example, I don't know if people know Zillow. Zillow is a web page where you can actually go to any location in the United States, click on any house, and it will tell you how much that house is worth. Right? And so that's interesting if you want to buy a house. You can look around and kind of check the neighborhoods, how much different houses cost, right? But it's a relatively hard task. So what they try to do is they basically say, how many bathrooms does the house have? What's the square footage, right? What's the proximity to the schools? What's the ranking of the schools, etc., right? All these kind of different features. So these are the feature items that I have in my vectors, the different dimensions. And I try to predict how much the house sold for. And whenever a new house gets sold, I basically add that to my data, and I retrain my algorithm. Right? So, but the answer could be anything between 0 and, I don't know, a couple millions theoretically, I guess. Another one is like, for example, if you would like to predict the height of a person, right, or the age of a person. All right, good. Any questions about classification versus binary, regression versus classification, etc.? All right, good. Yeah.
Could you send more notes back? I think this is
I cannot. I don't have more. Does anyone have 2, 3? You're not allowed to sell them. I will post them on Piazza. How about this? And you can just print out your own. Who does not have one? Raise your hand. Oh, that's terrible. They're all I see. They're all in the same location. You can't even look at your neighbor. Okay, if someone's really nice, you could just pass it back and then look at your neighbors. But it's only 3 minutes anyway left. Okay, so that is y, right? So basically we have our x and we have our y. So y is what we're trying to predict, and we just says kind of either be, a set of numbers that we're trying to shoot for, -1 or 1 or 0, 1. Can be, k numbers, that's, multi-class classification, or it can be real numbers, if you want to do regression. Now, what about x? Let me give you some examples of x. And, well, let me give you, first one is, for example, patient data. Right, so one thing that's really, really big nowadays, actually, well, it won't be anymore, I think, but one part of the Affordable Care Act, I guess, was, there was a lot of incentives for hospitals to not discharge patients that then come back very, very quickly. Right? So that's generally not considered in the interest of the patient. Right? So if you basically get discharged from the hospital, but then a week later you have to go back in, well, probably you shouldn't have left the hospital. Right? And that's usually generates more costs for the insurance. And so basically, there were penalties for hospitals if the patients go back to the hospital within 6 weeks, I believe. There was some time period. So a lot of effort was made saying, predicting if a patient will come back in the next 6 weeks. Right? So is the patient healthy enough that he or she can be 6 weeks outside on his or her own and do fine? But because then after 6 weeks, you're probably good. Okay. And so what you could do is you could basically say, well, my xi is basically the specifications of this patient. So one thing you may want to stick in is the here binary feature 0, 1, are you male or female, right? So it could make a difference, who knows, right? And the other one is the age, right? So, you know, here's like the person's 76 years old, right? It's the age in years, right? So that's another way of describing. Here's the height, right? 183 centimeters. Of course, you know, you don't know what that means, but you know, you're 6 feet or something. I don't know how many hands. I don't know. Some, you know, height in centimeters, yeah, you know. And you now basically, let's say you have some blood pressure and, you know, heart rate or whatever, and now you try to predict basically, will the person come back, yes or no, right? And you just take historic data from people that did come back or did not come back, and you train your algorithm that way. So another very common one is text documents. All right, so here you have an email, for example, and so that doesn't look like a vector. That looks like, you know, a string of numbers, sorry, a string of words. So what people do is they have something called a bag of words, bag of words, or bow representation. But you basically say, well, word order is overrated, right? Just, you know, who cares about in which order you put the words down? Let's just only look at the word occurrences, which words are in the text. And turns out that works surprisingly well. So, and then you can actually take the following. You can take a vector that basically is d-dimensional, where d is the number of words in the English language, for example. Right? So I don't know how many words there are in the English language, maybe 1 million. Right? And so then you start with the first word in alphabetical order. It doesn't matter, right? So ant, right? And down here you have zebra, right? And so then for every single word in your email, for example, you just say how many words that occur. So for example, the word the, you may have 5 times, right? And the word moose, right? 7 times, right? So I don't know, something like this, right? And no, right? And zebra you didn't talk about, etc. Right? So that basically you just count the words in your email, and that is a vector of just word counts. And that is a vectorial representation of your email. Turns out that works surprisingly well. So that's an easy, you know, usually you can identify if an email is spam or not spam, or a news article, you know, if that's politics or sports, right? You can detect that very well just in this representation, which makes sense, right? So if you talk about baseball or pitcher or something, it's probably sports. You know, if you talk about Washington, D.C. or president or something, it's probably politics. Why don't we leave it right here? And I see you again on Monday.